In this section, we'll discuss the first step of CLASLite, calibration to reflectance. The objective of this step is to convert the data registered in each pixel of land cover by the satellite sensor into surface reflectance values that we can use for mapping. The first step is radiometric calibration. In this step, we convert the data recorded for each pixel into units that we can use quantitatively. These data represent the intensity of solar energy reflected from the land surface and the atmosphere before reaching the sensor. CLASLite uses conversion factors called gains, obtained from the providers of satellite sensors, to convert units of digital numbers into units of radians. Here is a raw file shown next to its radians output. Normally, the user would not see this, since it is not the final output of step 1. Radians is a measure of the energy radiated by the sun that reaches the sensor, expressed in watts per square meters per solid angle. Although the raw and the radiance images look the same, the images statistics are clearly different. As you can see, the raw data is stored in units of digital numbers ranging from 0 to 255. In contrast, the radiance data is stored as a percentage in integers ranging from 0 to 10,000, where 10,000 is equivalent to 100%. The second process CLASLite runs in step 1 is atmospheric correction. As radiated energy passes through the atmosphere, it interacts with atmospheric constituents in ways that influence the reflectance value recorded for each pixel. Here, the goal is to minimize the influence by removing, to the extent possible, the effects of these interactions. The main atmospheric players are aerosols, water vapor, and other gases like oxygen and ozone. These constituents scatter and absorb radiated energy to various extents at different wavelengths. This means that the sensor cannot detect everything that gets reflected off the Earth's surface. CLASLite uses the 6S radiative transfer model developed by Eric Vermont and his team to simulate the Earth's atmosphere in each satellite image. It does this by looking up reference tables of data from MODIS sensor, which provides nearly daily global coverage. It then removes the best estimated model of the atmosphere from the image. The CLASLite team has automated this integration of atmospheric water vapor and aerosol data into the 6S code. So, when CLASLite is processing a given image, it uses the monthly average measurements that correspond to the image's date. The result is an atmospherically corrected image in units of surface reflectance. Surface reflectance is a measure of the fraction of incoming radiant energy from the sun that is reflected by the Earth's surface. This is the value we want to work with because it allows us to study changes occurring in vegetation and other land cover at Earth's surface. After atmospheric correction has been completed, we have our reflectance output. Reflectance, like radiance, is expressed as a percentage. Though the two images may look the same, we can see that the red, green, and blue band values for any given pixel differ. In some cases, the atmospheric correction model does not work perfectly. For example, in shaded areas or areas obstructed by heavy aerosol content, the reflectance value may turn out to be negative. In contrast, some pixels can exceed 100%. This can happen if the atmospheric correction model fails to remove radiation reflected off the atmosphere as opposed to the land surface. Aside from the atmosphere, there are additional barriers to the ability of the satellite sensor to collect information about radiant energy reflected from the Earth's surface. CLASLite deals with these barriers by masking them out at various steps. We'll discuss this in further detail later.